All right, well, welcome. Sorry for the delay getting started there. Um, Today I wanted to finish that example we had gotten started last time where I pointed out if you have an alternating series, there's a particular test for seeing uh, a bound on its error, and there's a nice example like this in the homework that's not too trivial, I think, so I want to make sure I covered it. Suppose I have the sum. Let's try this one. K equals 1 to infinity, or let's say n. 1 over n plus 1, n plus 4, left something off of here, times minus 1 to the n, say n plus 1. So that's an alternating series then, right? If you take all the way the minus 1 to the n plus 1, you've got all positive terms because n plus 1 and n plus 4 are positive, but this makes it alternate signs. And so now the question is, how many terms must you add together, say, in your hand calculator, to get an estimate of this number S, that's the sum of the whole series, to estimate S with error less than or equal to 10 to the minus 5. Suppose I had that problem, right? How many terms do I have to add up, right? And what we said was that the error for an alternating series, where it goes plus minus or minus plus minus plus, in absolute value, right, it can be positive or negative error, is less than or equal to the next term in the series. Right? Because you're going to add that over to one side, and then you're going to subtract something off, and you're going back and forth and back and forth. The total sum is moving back and forth. Here's S1, maybe. Here's S2, the sum of the first two terms, some of the first three terms, some of the first four terms. Because the terms are decreasing in size, you're converging, going back and forth, converging on a limiting sum S. And always, this is bracketed between what you're at and the distance to the next term. So, in other words, to write it out more formally, S, the sum of the series, minus Sn, the sum of the first n terms, that error is less than or equal to, well, they called it B last time. If I call this, I'll write it out, is less than or equal to Bn is the letter that the book uses, for a sum of the series that's B1 minus B2 plus B3 minus B4, alternating in sign like that. And I forgot the plus 1 here. It's less than or equal to the next term. So you add up the first n terms and estimate S. The difference between those is less than or equal to the next term. So that's the formal statement of the estimating sum. You can add up the first capital N terms with error less than or equal to the next term. So let's try it for this series. what you have here is we need remember Bn is actually the absolute value of the nth term, and so the absolute value here is 1 over n plus 1, n plus 4, right? Now, when will the nth term be less than 10 to the minus 5? We need b, what can I call it? K. Let k equals n plus 1. If bn is this, then bk is 1 over k plus 1, k plus 4. Less than or equal to 10 to the minus 5 with k equal n plus 1. So we've added up the first n terms, and then the n plus first term is bk or bn plus 1. The only reason I write bk instead of bn plus 1 is so I have less writing up ahead. So suppose we want the next term, bk, to be less than or equal to 10 to the minus 5. How do we achieve that, right? We can do it as follows, right? We turn this upside down. That means equivalently that k plus 1 times k plus 4 is greater than or equal to 10 to the 5th, right? If this positive number is less than or equal to this one, then the reciprocal of the left is greater than or equal to the reciprocal of the right. So we need that. Well, this actually then can be rewritten as k squared plus 5k plus 4 greater than or equal to 10 to the 5th, right? And that's a quadratic equation, so you can solve it with the quadratic formula. Let's write it as k squared plus 5k plus 4 minus 10 to the 5th greater than or equal to 0. When is it equal to 0? So this equals 0 for, by the quadratic formula, k equals minus 5 plus or minus square root 5 squared minus 4 times 1 times 4 minus 10 to the 5th. Sorry, I know I'm blocking you over here. I got this wire, so if you need to move, move. 4 minus 10 to the 5th all over 2 times 1. So there's the quadratic formula. And now do we want plus or minus? Well, there's two solutions to this equation, but we want the positive one, right? The minus one is nonsense. We're not summing in negative. So it's with the plus sign. And now you say, therefore, we need k at least this big to make the left side, right? This is a parabola if you plot it in k versus y equals this function space. So it's a parabola up. This expression will be equal to 0 when k equals this number and greater than 0 because the parabola is up for k greater than that number. So we need k greater than or equal to this number, but this one comes out, if you run it in your calculator, to be 313. So therefore, choose k, which was n plus 1, greater than or equal to 313, right? Which is what this comes out with the quadratic formula, or equivalently, n greater than or equal to 312. So there's a homework problem like that. I think it's good to at least do one of these. This is what people have to do when they actually apply these in computer courses, for instance, right? You want to make a series approximation. You add up a certain number of terms. That's what you can do for an alternating series. We're going to come up with another one for series that are not alternating shortly. Any questions on that one? That's kind of a long one. I'm sorry I had to erase part of it already, but I think I have the major part left. Okay, I can probably hear you online if you want to ask questions too. Take the mute off and put it back on. All right, so that's the beginning problem for today. And now I got to wake you up again because that's probably a dull one still. Even if it's a hard one for the homework. I'll probably ask you something like that in the first test, on the next test, and which I think is in 2 weeks, right? 2 weeks from today. The next topic, we're all done with just series. We're going to do something related to that called power series. And before I get going on that, I wanted to make one interesting comment on the series that pertains to these, because these are going to start at n equals 0 instead of n equals 1, all right? And maybe that makes a difference. Does it matter what index you start at? Suppose I did this sum, AK, some numbers AK, indexing K from 0 to infinity, and then I did this one, sum K equals 1 to infinity. Does this series have more terms than this one? Technically, to a mathematician, these have the same. I'll ask you a question here. Suppose you were over at the football stadium for a game, and it was really packed. So you wanted to know, are there more people in the stands, or are there more seats in the stands? How would you find out? What's an easy way to find out? Maybe you got the megaphone, you can talk to the people. Counting take a week probably, right? Have them all sit down is supposed to be the answer. If there's seats left over, and you say, oh, there's more seats. But if there's people left over, you say there's more people, right? When we deal with infinite sets of numbers, we do the same thing in mathematics. When we make this list of numbers, 1, 2, 3, 4, 5, etc., for these indices, this is an infinitely big set, right? This is called the set of natural numbers. Maybe I'd call it n or something. Set of natural numbers is an infinite set. We'll say it's of size aleph naught. Well, it's chi naught there, but I can't draw an aleph. But anyway, so it's got a certain size. It's an infinite set, right? For a set of like this one, the letters A, B, C, we say that's a set of size 3 because it has 3 elements. But we give a letter to this that's aleph naught. You can look it up online, and they can draw it better there. And what about this set now, the set of whole numbers? Maybe I'd call those W. That's 0, 1, 2, 3. Maybe this is a bigger set because, after all, it's got all of these elements plus 0, right? But in mathematics, we actually say those are the same size because of the stadium problem, right? If we pair this one with this one with this one, we pair each number in this list with the number in this list that's 1 greater, we actually find we can put them in one-to-one correspondence. And so infinite sets will say they're the same size if they can be put in one-to-one correspondence. These are the same size. Maybe you say it doesn't make sense. This has all these elements plus one more, but imagine going to a foreign country or something, and the things they write down are ziddle, twiddle, dot, and flim flim or something. And how do you decide which one's bigger? Well, you just pair them up, right? And decide if they're bigger. And so then you realize, well, wait a minute, if flim flim mathematics it can be paired with both of these, it must be the same size as both. So we say these two are the same size because they have the same number of elements. And this leads to interesting conundrums. For instance, Z, the set of all integers. What is an integer? Oh, come on. Everybody knows what an integer is in your class. You learned it in algebra, right? I just scared you probably. That's all numbers with nothing after the decimal point. It's 0, 1, minus 1, 2, minus 2, 3, minus 3, etc. That's an infinite list. Maybe that has more elements because it's got all of these. It's got infinitely more, right? But actually, you can pair these up, right? You pair this one with this, this with this, with this, with this. I mean, you can write a function that pairs them up, actually. It's not too hard. But these can be put in one-to-one correspondence, and so the set of all integers is actually the same size. And amazingly, now you go to look at the rational numbers, Q. What are the rational numbers? Nobody took algebra? Those think yeah, fractions. Think of ratios, rational ratios. So the set of all m over n such that m is an integer, let's say, and n is a natural number. So this means m is an element of the set of integers, and n is a element of the set of natural numbers. You can put a negative on the bottom too, but it just repeats some of the values. Now some of these are the same, like 1/2 and 2/4 are the same, so some of these are equal. But even so, actually, this turns out to be the same size. This is one of the things you want to learn in calculus, to have intuition for this kind of stuff. So even though this isn't on the homework, I wanted to present it because it will give you a better intuition on these series here. If I make a table of m versus n and I construct all the fractions where the top can be 0, 1, -1, 2, -2, and the bottom can be 1, 2, 3, 4, and so on, the natural numbers, then I can make these ratios. This is 0 over 1, 1 over 1, -1 over 1, and so on. And then 0 over 2, 1 over 2, and so on. And so some of these are equal, like all these zeros are equal. We could just count that one once and get rid of these. But even so, look what you can do. You can pair these up. Pair this up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can weave through here and put them and pair them up with the natural numbers again, right? 1, 2, 3, 4, 5, 6, 7. And in this matter, you can make a function that puts these rational numbers in one-to-one correspondence with the natural numbers. This is actually of size aleph naught also. All these are the same size. That makes you think maybe all infinities are the same size. If you get an interest sometime, we can actually show that the set of all real numbers is actually bigger. There's always real numbers left over no matter how you try to pair these up. And it's actually a pretty nice intuitive proof without going into the details. Pretty easy to do. The reason I introduced this, can you guess why? That all these sets where you just make a list forever like this are the same size infinity, but we'll run into other sets that are bigger, mostly the real numbers, is this. Some of these infinite sums, we're going to do this. We're going to start at 0 instead of 1. It's the same list of numbers. The set of infinite sums you can write like this is the same as the set of infinite sums you write like this, because it's just k is just an index, right, in either case, and it runs over a set of the same size, so you get the same results on everything. It doesn't matter if you start with 0 or 1. You can do this. Some of these ones will go k equals 2 to infinity with k even. That's the same size, right, because the numbers 2, 4, 6, 8, they can be put in one-to-one correspondence with 1, 2, 3, 4, right? Just every number goes with its double, right? And so this one gives you exactly the same set of infinite sums you get from this one or this one. Starting any place you want, you can run over all the energies. You can even run over the fractions if you want. All those things amount to looking at the same possible lists of infinite sums. So that's the point here. And now we want to move on to power series. That's just to pique your interest a little bit, because we are going to have sums over different things. We're going to make this definition for a power series now. A power series in a variable x and using a constant c is an infinite sum. K equals 0 to infinity. We can start at 1 or wherever we want. It doesn't matter where you start. AK x minus c to the k. That's the definition of a power series. And you notice it's got a variable in it. And what happens is you get a different series for each value of x you put in, right? You can put a different x, and each one gives you a different series. And so what happens is this might converge for some value of x and not for others. But that'll be called a power series. It's not a series, but it becomes a series when you plug in a value for x, right? So, and we'll start with 0 because it turns out to be convenient later. And then there's this wonderful theorem that comes up, and it can be proved with a ratio test for the convergence of power series. If you put, it doesn't matter which x value you, it doesn't matter which c constant you pick, it has the same theorem. A power series call it 1 here, converges either, I'm going to write this out in a little more detail than the book does, 1 only at 4 x equals c. In other words, the only number you can put in there that'll make it converge is if you put in x equals c. You put anything else, it diverges. So that might happen, right? You get a power series for each value of x you put in there. C is a given constant. And sometimes, no matter what x you put in, it diverges. Unless you put in x equals c, then obviously it converges. What happens if you put in x equals c? You've got c minus c to the 0, and that's assumed to be 1. We'll say, even though it's 0 to the 1 the way it's written, with the notation is supposed to mean that if you put in x equals c, this is 1, because it's 0th power. And so you just get the one term, a0 times 1. It's just a one-term series, and of course it converges. All the rest of them aren't even there, right? Because c minus c to the first power is 0, c minus c to the second power is 0, right? It's just 0. But the first term, a0, remains. So it converges and just gives you the first term if x equals c. And we say then that r equals 0 is the radius of convergence. I'll write the radius of convergence later. But we'll say that because it converges only at a point, the distance it converges from that point is 0, is the idea. The other thing that can happen, it can converge on the interval c minus r to c plus r. This r is not the real numbers. Remember, if I'm writing the real numbers, I'll write this symbol with double bars here, or the book will make it boldface. I just can't do that on the board. It takes too long, right? So these things will mean the set of real numbers, but r here is a number. It's called the radius of convergence. And it will converge on some interval c minus r to c plus r, a symmetric interval about the point c, with r greater than 0 finite. Or, finally, it may converge on minus infinity to infinity. Every real number it converges for. That's common also. And in this case, we say r, the radius of convergence, is infinite. That's the theorem for power series. That's kind of an amazing result, don't you think? Then on each of these, it diverges otherwise. No, I'm not. I need to. That's not quite right, because this one doesn't diverge at all. I need one more line in here. I should have put it in. My apologies. On minus infinity to infinity, and we say that r, the radius of convergence, is infinite. And in the second case, it converges on this one and diverges on the interval from r to infinity and on the interval from, not r to infinity, c plus r to infinity, and on the interval from minus infinity to c minus r. There we go. And you notice something's left out. What if the endpoints here? What if the point x equals c plus r and the endpoint x equals c minus r? The theorem doesn't say anything about that. And the reason is that sometimes it converges there and sometimes it doesn't. But that's an interesting thing because it amounts to these three pictures. And let me write it down. R is then called the radius of convergence, we said. And here's the interval of x values for which you get a convergence series in the three cases. All right? 1, there's a number c that's in the series, right? You write, this is what the series looks like. It's sum k equals 0 to infinity, ak, some set of list of numbers, x minus c to the k. And it converges only for c, and it diverges everywhere else for other x values. The other possibility is that it converges at c and on an interval of width r to each side. So you go from c minus r, this distance r over to c, and then the same distance r to the other side to c plus r. So it converges on this interval at least, omitting the endpoints, and those values of x it converges for. And then it diverges on this interval over here and this interval over here. And in this case, it diverges all over here and all over here. So I've shaded the places where it converges, except these 2 points right here, we don't know. Sometimes it converges and sometimes it doesn't at those 2 points. That's the idea. But isn't that interesting? It always converges on a symmetric interval, r units this way and r units that way. Now do you see why it's called the radius of convergence? This is a one-dimensional circle at C, right? The circle at C is 2 points at C minus r and C plus r in one dimension. It's a set of all points on the number line at a distance r from C. So it's a circle of radius C. So it converges inside the circle of radius C on the disk of radius C, you can say. And it diverges when you go past C. But at C, along the circle, at the circle of radius r, it may or may not converge. That's the idea. And then finally, case 3, you just shade the whole number line, right? It converges for all values x. Questions on that? Rather than doing the proof, I want to do some examples then. But when you see the examples, you begin to realize why I said before the ratio test is probably the most important one. The ratio test is what you use to establish this radius of convergence for various series. Here's a very important one here. I say this because some of these power series I want you to memorize. What is the sum? This is a power series. 1 plus x squared plus x cubed. Do you see that's a power series that goes on forever? You can also write it in sigma notation like this. Sum k equals 0 to infinity, 1 times x to the k, right? Each coefficient ak is 1, right? This is a general power series of sum ak x minus c to the k. So here all the ak's are 1, and c is equal to 0 where you have x minus 0 to the k. So it's a power series at the point c equals 0, the origin of the real number line. And each coefficient is equal to 1. So it's kind of a real simple series. Maybe it's kind of important because it's so simple, right? What does that add up to? If you think about it for a second, we've already shown what this adds up to. It adds up to a very interesting function. X is a variable now, but still we can figure out what it adds up to. Can you see what it is? What kind of series is it? Yeah, it's geometric. Awesome. The first one is A in the geometric series, and you notice you multiply it times x, times x, times x. Every one is x times the last one. It's the same number times this one. So this is a geometric series with a equal 1 and r equal x. We recall that this adds up to what then? there's two cases. It adds up to a over 1 minus r, which is 1 over 1 minus x, if what? Remember? The absolute value of r is less than 1, right? Which in r is equal to x, so it's absolute value of x less than 1. So we'll make a piecewise definition here for its convergence. It can add up to 1 over 1 minus x if the absolute value of x is less than 1. And then it does not converge, it diverges otherwise. Absolute value of x bigger than or equal to 1. I'm sorry I have to write kind of small there. But the geometric series theorem tells us that this actually adds up to an interesting function. And it turns out that these power series, a lot of them add up to interesting functions. For instance, e to the x. There's a really easy power series that you can add up for e to the x we're going to see. There's another easy power series for sine x. In the early days of calculators, they would use some of these series, to add up. If you wanted to calculate the sine of 0.1, how does your calculator do it? Well, it does a bunch of arithmetic adding up terms. Now they use more complicated series, but a lot of these calculators, they don't use these simple ones we'll do in this class, but they tend to use some sort of series approximation. They add and multiply a bunch of terms, and they cut it off somewhere when they know the error is small enough, like when we knew in the alternating series case, we could get error less than 10 to the minus 5 if we added 312 terms together, right? So they'll find a series that converges faster, and that takes a lot less terms. But a lot of calculators and so forth, or you go on these software packages like Mathematica, and they'll have series to add up these special functions. And that's what they're doing. They're just doing a whole lot of arithmetic with some sort of power series or maybe some other series. There's some other series that you study in higher mathematics. But here's a series that adds up to this function, 1 over 1 minus x, if absolute value of x is less than 1. All right. Now, what does that tell us? What is the radius of convergence? Well, look at this interval here. The interval of convergence is absolute value of x, right? Less than 1. Since we have convergence for absolute value of x minus 0 less than 1, I'll write it that way. That tells us, right? Remember, c is equal to 0. Using the theorem for convergence of power series with c equals 0, that tells us that the radius of convergence is 1. Because that statement I wrote down, c minus r less than x less than c plus r, that was the interval of convergence in the second case, is equivalently absolute value of c minus r, absolute value of c minus x less than r. So what I wrote in there was equivalently this, and so when you get when you see this, rewrite it like this and say, oh, that just means, I wrote this backwards. I guess let's write this as 0 minus x. It doesn't matter. So c minus x with c equals 0 for this series, because we made a series in powers of x minus 0. You deduce that the radius is 1. The other way to do that is just draw the interval. You can draw the interval and say c is equal to 0, and it converges from minus 1 to 1. Sketch this in. This is called the interval of convergence. And then you see, oh, it converges 1 unit to that side and 1 unit to that side, so r is 1. So you can draw the picture and see what r is. Or you can rewrite this kind of thing. Absolute value of x less than 1 as this kind of thing, and say, oh, that's this. That's the interval we had. All right, so this has radius of convergence r equals 1 is the point, because it converges 1 unit to each side of that central point c equals 0 in this case, right? And then this one would be called the interval of convergence. So the homework problems will ask you, what is the radius of convergence? That's how far on each side of 0 it converges here. And what's the interval of convergence? It's this interval. And you don't include either endpoint, you notice, because right at the endpoints it says it diverges in the theorem. This is the whole interval. See how we're doing on time here. I'm sorry, I don't have my, I need to get my clock out here. There we go. So we're running a little short on time. Let me do another interesting example. We'll pick this up next time. This one is going to take at least 2 lectures to finish. Notice the homework isn't due for a while on this one. But you can see there's a lot to it. Suppose I gave you this series here now. Find the interval and radius of convergence for this one. Sum x to the n, and this is just like one of your homework problems, actually, I think, n 2 to the n equals 0 to infinity. So I'll change the index and call it n instead of k, but it's the same thing. It's just a dummy index. It's saying it's indexing the numbers you're adding up. But the actual series looks like this, right? Here's a power series, and the first term when n equals, oops, wait a minute. I guess this one went from 1 in the book. Don't want to divide by 0. You can start, again, from any index you want. It's typical to start at 0 for reasons that we haven't seen yet. So the first term is x over 1 times 2. So it's x over 2. Then I put in n equals 2, and I get x squared over 2 times 2 squared, and then plus x cubed over 3 times 2 cubed, plus so on and so forth forever. And for each value of x, it gives you a power series, right? It gives you a series. So this is a power series in x minus 0 again. If you think of this as x minus 0 to the n, right, then you think this is a series with c equals 0. So it's going to converge in some symmetric interval about c equals 0 on the x-axis, just like the last one did, in a symmetric interval about the origin. And what interval is this that it works on? This is where the ratio test comes in. Because these power series always have powers of n and frequently have powers down here, and it turns out later frequently have factorials, powers and factorials were precisely what the ratio test works really well for, right? So usually to find the radius of convergence on these, you use the ratio test and you say rho is the limit as n goes to infinity of the ratio of successive terms in here, and you just leave x variable. And so we've got absolute value of x to, we'll do this at n plus 1 first, right? The n plus first term, n plus x to the n plus 1 over n plus 1, 2 to the n plus 1. That's the n plus first term. Divided by the nth term is x to the n over n times 2 to the n. So there's the ratio test. And where that's less than 1, we get convergence. Where it's greater than 1, we get divergence. Where it's equal to 1, we can't tell, right? From this test, we have to do it another way. So we multiply the top times bottom over middle times middle from algebra, right? And we say, oh, it's n times 2 to the n, the bottom, times the top, x to the n plus 1, over middle times middle, n plus 1, 2 to the n plus 1, x to the n. Absolute value, right? And what we'll get is this then, right? X to the n plus 1 over x to the n just leaves x, right? That's just x. 2 over 2 to the n plus 1, 2 to the n over 2 to the n plus 1 is just 1/2. And then we've got the n over n plus 1 left. So this is limit as n goes to infinity of absolute value of n over n plus 1 times x over 2. So what's the limit of that? It's actually really easy. The x over 2 comes out because it's a constant, right? We're just letting n change in here. So this is actually absolute value of x over 2, limit n goes to infinity of n over n plus 1. That's positive, so I can drop the absolute value. And this one is 1, right? I can put equals 1 if I circle limit, can't I? So that it's going to absolute value of x over 2. What does that tell me? If that's rho, we know this converges for rho less than 1 and diverges for rho greater than 1. So converge on the interval where x over 2 is less than 1, diverges, right, when rho is greater than 1. That's the interval where x over 2 is greater than 1. But wait a minute, that's equivalently absolute value of x less than 2, and this is equivalently absolute value of x greater than 2. If you draw the interval out again, this is the interval of convergence. Again, the central point C equals 0 because we did a power series in x minus 0. But we go 2 units to the left and 2 units to the right between minus 2 and plus 2. We must be out of time, I'll bet. It's sort of looks like we're out of time. And we converge on this interval here. That's what the ratio tests tell us. But well, what about the endpoints? Maybe I'll have to do those next time because I'm out of time. It turns out it converges on one side and not the other. I think it converges on this one and not on this one. So the interval, the ratio test tells you the interval, the radius of convergence, but you have to check the endpoints separately. We'll do that next time. Thank you for coming today.